All right. Hello, everybody. Good morning, good afternoon, good evening. We are going to do section 4.3, which is actually going to be a relatively quick section because we've already done most of the work in 4.1 and 4.2. Now, just a quick recap of what that was. We started by looking at difference equations like this one, where we define this like sequence of vectors where every next vector in the sequence you get by doing a matrix times the previous vector. And we saw how that could model a lot of real life situations. And it's a pretty useful thing in applications of linear algebra. And how that is equivalent to saying, like, the nth vector in the sequence is equivalent to just doing a to the power n, because you're basically multiplying by a n times, but starting with the first vector, p0 in this case. But also that taking powers of matrices is computationally intensive. It's tedious to do all that multiplication and addition. And if you have big matrices and big powers of n, it becomes unfeasible. And then we saw that if you diagonalize a matrix by finding P and D, a diagonal matrix D, so that A is equal to P times D times P inverse, that makes that a lot easier. We get that A to the power n can be written as P times D to the power n, which is easy to compute, times P inverse. And we could express that using the diagonal coordinates theorem. And we saw how that works, that like once you know the b1 and b2 vectors, which are like the columns of P here, then you can see what the pattern is when you do powers of A times some starting vector. And then in 4.2, we realize that those columns of P that we're talking about are the linearly independent eigenvectors of A, which correspond with the eigenvalues in the diagonal of D. That's using this definition of eigenvectors and eigenvalues, where your matrix A times an eigenvector is equal to the eigenvalue scaling that vector. So now let's actually look at how you can just start with a matrix like this A here and find eigenvalues and eigenvectors of it. We're going to start by showing that 2 is an eigenvalue of A by finding a corresponding eigenvector. So, in other words, the goal is to find a vector x so that a times x equals 2x. And, how would we do this? Could we, like, subtract 2x from both sides and get ax minus 2x equals 0? Sure. And then maybe we could, like, factor out a minus 2. That looks reasonable. And then divide by a minus 2 and get x is the 0 vector divided by a minus 2. This looks reasonable, but a lot of these things are undefined. Like, for example, a minus 2 is not a thing. That doesn't exist. Also, whatever that is, dividing a vector by something, what's going on here? So this doesn't really work, but this does almost work. We just need to make a little modification to this idea. And that modification is to notice that 2 times x is the same thing as 2 times the identity times x. So let's just be explicit with actual numbers here to see what I mean by that. So here's a times x, which is x1, x2, and we're doing that minus 2x1, 2x2. But I don't want to write it as 2x1, 2x2. I want to write it as this matrix with 2, 0, 0, 2 times x1, x2. that's the same thing as like 2 times x, right? You just get 2x1 plus 0 and 0 plus 2x2. So that's the same thing. And now we can factor out the x from this in a way that makes sense. Like so. And we could then just subtract the two matrices here, and we have a regular old homogeneous equation like you just solved in the warm-up. So negative 2 minus 2 is negative 4, 3 minus 0 is 3, negative 8 minus 0 is negative 8, and 8 minus 2 is 6. And so this is equivalent to the system of equations with augmented matrix like so. And we can row reduce this. I'm going to replace row 2 with negative 2 row 1 plus row 2. That's going to be negative 2 times negative 4 minus 8 is 0. Negative 2 times 3 plus 6 is 0. Leave row 1 unchanged. We could also just scale row 1 to get it all the way to reduced echelon form by dividing by negative 4. And so we have x2 is a free variable. So when we want to write the solution set of this, we can say the vector x1, x2. Well, x1 is 3/4 x2, and x2 is just x2. So we can write this as x2 times 3/4 1. So any multiple of this 3/4 comma 1 vector here is going to be an eigenvector corresponding with lambda equals 2. These are some examples. You should point out that 0, even though it is a solution of this homogeneous equation, is not an eigenvector, because the definition of eigenvectors is they're not allowed to be 0. But any other non-zero solution of this equation, any other vector x that makes a times x equal to 2x, is an eigenvector. All right. In the next video, we'll see how this works in general, how you can find eigenvectors once you know an eigenvalue, and that we're basically just finding vectors x that are in the null space of this matrix here, and relate the null space to determinants, like you reminded yourself of in the warm-up, and see how you can use that idea to find eigenvalues, even if the problem doesn't give you them to start. So we'll see how to find eigenvalues in the next video.